Let us look at another Leetcode problem, aliens dictionary. This is also classified as a hard problem in Leetcode. So let's go and read the problem first, a bit quickly. That's what the problem says is there is an alien language that uses English alphabet, and however the ordering of the among the letters is unknown. So basically we don't know how the letters occur. Like we already know in the alphabet A, B, C, D occurs in this particular sequence. And it has been given to us a set of words which are sorted lexicographically in the aliens dictionary. Then we have to basically figure out what is the lexicographical sorting of the characters in this alien dictionary using this information. Okay, let's go back there. So I've copied this one and take this as an example and try to figure out what we can do from here. So what's the maximum information what we can extract from this given information? So I would say if we compare these two, anyway, if you are being given two words and asked to compare how it is WRT and WRF in a dictionary, what you generally do is we compare every character by character and we find the first differing character, right? And if T is before F in a dictionary, then we say, okay, WRT occurs before WRF. So this is the information what we can get from this given set of words. So if I get this and I try to extract this information from this example, let me just clear this out. Then what you can write. So if I compare these two words, what I can say is WRT and WRF. Then from this I can get the information that T occurs before F, right? And if I compare WRF and ER, I can be sure that W occurs before E. Then I compare the third pair is ER and ETT. What you can get from here, E and E are same, R and T. So R occurs before T. And the next one is RFTT. Before this is ETT. And from this you see what we can get the information is E occurs before R. Right? And the solution given here is WERTF. So just let's write the solution as W and then occurs E and then occurs R and then T and then F. One thing, if you formulate this given information as a graph, how it will look. Suppose I say T has an outgoing edge to F, a directed graph. Then there is a W and has an outgoing edge to E. Then there is a R that has an outgoing edge to T. And then there is a E which has an outgoing edge to R, right? So I think it will be nice to draw it here. So we had W that has an outgoing edge to E and E has an outgoing edge to R. Okay. Let me ask you, how will the topological sorting of this graph look like? And what is topological sorting? Let me explain it a little bit quickly. And if you want to have a little bit deeper knowledge about topological sorting, you can look over online resources as much as you want. So what happens if you want to do a particular task and you know that you have to take things in a particular sequence, right? So for an example, a topological sorting can give you a way in which you can do a sequence of steps, you can say, in an algorithm or in any situation in which you have a dependencies, so that the previous steps are basically dependent on the current steps maybe, and the current step may be dependent on the step what you are going to take on the future, so that at the end you will have a sequence of steps which basically gives you the exact outcome what you have. So suppose you want to plant a tree. Okay, so you want to plant a tree. At the end you have a pot and you want to plant a tree here. So what you go to the market and you buy a plant. First you go to the market and then you buy a plant. Okay, and then you go to the market again, and at that you can go and buy there from something like a pot. So you go there to the market and then you bought a pot. Then what you want, you also need mud. So you can go to the market and buy some mud. Okay, let's assume anything like this. So you go to the market and buy some mud to this. Now, how you can plant a tree? You can plant a tree by taking a step like take the bucket or the pot, and then you take the mud and then you put this together, right? So you in the here you put the mud, right? That's nice. And then what you can do, you can just take the plant and then you can plant the plant here, and then you will at the end get this one. So how you can do these steps? If I say this is step A, if I say this is step B, this is step C, and this is step D, and this is step E, then you can do either one possible way to do this is buy A, buy B, get C, and then do the D, and then you are at E. Or you can also do it like go and buy mud first, then get a plant, and then get a pot, and then go and put all things together, and then you are planted a tree, right? This is one possible way to do it. Exactly in the same way, you can say the topological sorting works. You can have another example like courses, right? In the university, if we have courses and the courses are dependent in a way that you have to pass a course in order to take the next course. For an example, suppose you have something like you have university course A, and then you have course B, and then in order to take the course C, you have to pass course A and course B. Then you have a course D. In order to take course D, you have to pass course C. Then you have a course E, which you can take it independently, but in order to pass course F, you have to pass course D and you have to pass course E. And then in order to take a course called A prime, you have to pass course F. Then in which sequence you can take the courses? You can take the courses in sequence like A, then you can take B, and then you can take C, and then you can take E, then you can take D, then you can take F, and then you can take A prime. That's a possible solution. And there are multiple possible solutions out here, right? Because you can take in a very different sequence what are the courses which are having no dependencies. That's how the solution to this problem, alien dictionary, can be multiple solutions you can have depending on what are the characters which are not having any dependencies, because that's the information what we can extract from this given sorted list. So we'll use an algorithm called Kahn's algorithm in order to find a topological sorting, and then we can deduce the solution to this problem. So it's K-A-H-N as Kahn's algorithm. Using this algorithm, we find the topological sorting using in degree on any node. Okay, let's go and take a rough example how basically this algorithm works. So what Kahn's algorithm does is basically calculates first the in degree of all the nodes. Okay, so the in degree of this node is how much it is? It is 2. The in degree of this node is 1. In degree of this node is 2. This node is 1. This is 0. This is 0, and this is 0. So after calculating the in degree, what Kahn's algorithm does, you take a queue and you put all the nodes which are having 0 in degree in there. Okay, so it was A, and then I put B, and then I put E. Now we take out each node from the queue. So supposedly A, then A is the first node from where our topological sorting starts. Supposedly this will go off, and then its in degree will reduce to 1. Then we take out another node which is B, and then we see all the nodes which is connected to this, and then we remove B, and then I reduce the in degree to 0. And once we see a node with an in degree of 0, then we push that node in the queue. So I have removed this, I have removed this, and then I push this to the queue. So C goes to the queue. Now we remove E, and when we remove E, we reduce the in degree of the node which was connected to it. So this will become 1, and this is removed. So next what we have here is E. And then there is nothing, no nodes which in degree at 0. So we take out C because C was having in degree of 0, and we put C here. And then we reduce the degree of the one to which it was connected to. So we get this one out. And then we basically see that D is now having an in degree of 0. So we put D to the queue. Now we take out D from here. And then we see basically, okay, the in degree of the node through which D was connected, F, then we make it to 0. And then we put F to the queue, right? And then we take out F from the queue and put it here. And then reduce the in degree of the node to which it was connected to 0. And then we put A prime to the queue. And then we at the end we take out A prime, and as a result, this is the topological sorting or what we get using Kahn's algorithm. We'll use the same algorithm for finding out the topological sorting of the characters in the Salient dictionary, which will be our solution to the problem. So let's go and write the solution on Leetcode. Okay, let's try to write the code. So from this given information, first thing what we have to do is build a graph, right? And we build a graph by comparing consecutive words in the given set of words. So I take an unordered map and key as a character and value as vector of char. And I call this as graph. The next thing what we have to do is save the in degree. And it's already given in the question the maximum number of characters what we have is 26 because it's lower English letters. So we can just take a vector, an array of size 26 to save all the nodes and their in degree. So I would say vector of integer in degree and size 26 and initialize them with 0. Let me take another function to build the graph. So I call this function as build graph and then pass in the graph and in degree. Okay, let me write this function now. Build graph and then it will take unordered map of char and vector of char, and we take it by reference because we have to build the graph because we are not returning anything. And then we take the another one which is the in degree, which is a vector of integer. We take it also by reference, and that's it. Right, now what you have to do in order to first build the graph. First thing, this graph will have all the characters, all the unique characters which are there in the whole given set of words, right? So if I say first thing is that we can loop through all the we also have to pass the words in order here because we need them. So that's here you say vector of string and words. Yeah, so first in the graph we will put all this as a key, all the characters which are there in this all set of words. So I would say for string word in words, and then for character ch in word, what do? You put graph of ch equal to an empty array, right? Then we'll have all the characters put in here. Now what we have to do, we have to compare one word with the other word consecutively, right? That's what we have to do. That should be very simple to do. So what we do here, we take a loop for int I equal to 1, I less than what's the total number of words in here, that's what we say. So let me save this information here. So int n is equal to words.size, and this loop will go till all the words n, and then I plus plus, and then we'll compare the first word and the second word. So I say the string first word is equal to words of I minus 1 because I'm starting the loop from 1 and the first one will be just one before that. And string second word equal to let me take it also as word equal to words of I, but that is the current one. Now we compare both of them. So what says, and we will compare till the length of the word which is of minimum among these two, right? That's the number of characters what we want to compare. So I would say size, how much we want to compare is minimum of std minimum and first word dot size comma second word dot size, and then we'll loop through them. Okay, so I write a loop for int I equal to 0, I less than, let's take this as idx less than size and idx plus plus. What do you have to do? If character does not match, that means we have got basically an information which we want to save in the graph. So I say if first word at particular idx is not equal to second word at that idx, then we have an information to save in the graph. And then we say graph of first word at idx, that's the character, dot push back what? The second one, right? So you say second word idx, and at the same time we have to save the in degree as well, in degree of the second one, right? Second word at idx plus plus, and this we have to say minus because we have to map it to the index in the array. And then we don't want to go further if we just get this information, because that's how we compare the first character in the two words which are different, and then we get the information that the character which lies before or after in the given dictionary or in the given alphabet. Okay, so that's the information what we can have here. And so we have built the graph. Now what we have to do, we have to take a queue and process, and in order to build the final topological sorting. So I would say string, let's say answer equal answer, just let's take it as a blank, and then we take a queue. So queue of characters, we say queue, and then we push to the queue all the characters which has an in degree of 0, right? That's how we start from. So for, it's easier to do it like this, auto el. So every element in the graph, and the first element of this each el will be the character itself, right? So I say if in degree of el dot first minus a equal to 0, then we push this in the queue, queue dot push el dot first, right? Easy. The next thing now what we have to do, we have to loop through this queue. So I would say while not of queue dot empty, I would say first auto, or it's a character we know already, so character cr current is equal to q dot front, then you say q dot pop, and then you have to add this character to the answer plus equal to cur. Now if we can take a boundary condition, if for this particular character there is no value in the graph, then we just have to continue, right? So if I say if graph dot find current character is equal to graph dot end, or let me take this in a bracket, or we see that the size of the vectors at that particular character, size of the vector at that particular character will basically give all the connections to that particular node is 0. So graph of current dot size equal to 0, then we just continue, we don't do anything, right? Else what we do, we basically go through all the connections. So I would say node in the neighbor to that particular current node, graph, and then I say current, and then we see reduce the in degree of that particular node by 1 as we talk in Kant's algorithm. So in degree of that particular character. So node minus a minus minus, and if the int degree has reduced to 0, then we push it to the queue. So if int degree of node minus a equal to 0, then push it to the queue. Q dot push, and then you say node. Nice. And see the brackets. It's done. And how we get the answer? So we'll return what we can check if this answer size to see if there's a possible solution or not, because if there is a cycle, then we will not have a possible solution. So if answer dot size is equal to graph dot size, because that's the total number of characters which is possible, which we have with the given information, right? If both the sizes are same, then we have found a possible solution. We return the answer, else we just return a blank, right? Let us try to run this now and see it works. That's fine. And if we submit it, okay, it fails in this particular case. If you see this closely, it's ABC and AB. So what happens is here, there's a first word is bigger in size than the second word, and the second word is a prefix of the first word. But in any particular dictionary, a prefix will always come before any other word, which will basically be the prefix of other words, right? So we have to take care of these cases so that we remove these cases and return an empty string whenever the second word is a prefix of the first word. So how we can take care of this is, so we can take care of this during building the graph itself. So if I take it as a return value, integer, and I take it here as an int, and during this case we compare the two words. So I say if first word dot size is greater than second word dot size, and we also have to see if it's a prefix, and we can do this in C++ by using compare. First word dot compare, starting from index of the 0, and then to the size of the second word dot size, and second word, and if this is equal to 0, that means it's a prefix, and then we say in this case return a -1. If everything is fine, then we return a +1. And here what we can do, we can just check the return value and say if ret is less than 0, then we return an empty string, else we just continue our process. Cool, let's submit this one now. Cool, it works fine, and it's fast enough as well. Okay, I hope the solution helped you to understand the problem a little bit more easier and better. And if it did, please do like and subscribe so that I can make more videos. Thank you so much. Bye-bye.